Hello students, we are going to start today the continued discussion of heat and thermodynamics, and we will be starting today the calorimetry. So the topic of our discussion is your calorimetry. Calorie. Initially, before 1942, heat, work and energy were treated as different quantity. Heat was measured in calorie, whereas work and energy was measured in joule. So what I mean to say that before 1942, heat, work and energy were different, whereas now we have understood that heat is a form of energy, and so heat, work and energy remains the same. So before that, what I would like to tell you, how the calorie was defined. Calorie was defined as the amount of heat required to raise the temperature of 1 gram of water from 13.5 degrees centigrade to 14.5 degrees centigrade. Sometime you will find in book that it is amount of heat required to raise the temperature by 1 degree C. That is also correct, but the standard definition is that calorie is the amount of heat required to raise the temperature of 1 gram of water from 13.5 degree to 14.5 degree centigrade. So we can understand this thing in a very comfortable way, that 1 calorie, it is the heat energy required to raise the temperature of 1 gram of water from 13.5 to 14.5 degree centigrade. This is the standard definition of your calorie. Now, when we understood that heat is a form of energy, naturally the joule is the SI unit of energy. Naturally there should be some relation between joule and calorie. So 1 calorie is 4.2 joule. This is basically conversion factor, and this is called experimentally. It has been determined that 1 calorie is equals to 4.2 joule, and this conversion factor is called mechanical equivalent of heat. And now we can understand that heat, work and energy all have the same unit, that is the joule. Now certain terms are related with calorimetry. Out of that, I would like to discuss the first term, that is a specific heat. So a specific heat, it is the amount of heat required to raise the temperature of 1 gram of material by 1 degree C. So this is basically the definition of specific heat, and you should understand a specific heat is the property of material. A specific heat is the property of material. So if we represent a specific heat by C, C is equals to Q by M delta T. Heat required to raise unit mass by 1 degree C. So what should be unit? Unit should be, in SI system, it should be joule per kilogram degree centigrade. In SI system, there are certain specific heat that you should remember, and out of that specific heat is generally constant. It does not vary with temperature, but sometime it may vary. There may be question in which it vary with temperature, that I will try to solve you with the help of example. You should understand certain standard value you should remember. For example, a specific heat of water, 1 calorie per gram degree centigrade. This value you should remember, and by conversion you will find that it will be 4200 joule per kilogram degree centigrade. Certain specific heat, a specific heat of water. Then a specific heat of ice, you should remember 1 by 2 calorie per gram degree centigrade. Similarly, this is the value of your steam also. Steam also is this one, and if you will convert it into joule, it will be coming 2100 joule per kilogram degree centigrade. These are the certain value that you are supposed to remember by yourself, and you should not be dependent on the examiner that he will be giving these values for your calculation. So these values are the standard result which you should remember all the time. Let us take an example that there is a vessel in which 2 kg of water is there. Temperature we are changing from 5 degrees centigrade to 10 degrees centigrade. What is the heat amount of heat required? Amount of heat is equals to how much? In this question, you can see Q is equals to ms specific heat into delta T. So M is your 2 specific heat, as it is in kilograms, so we can write 4200. Delta T is your 5. This way we can discuss. So a specific heat is equals to, so the amount of heat required to raise the temperature of 2 kilogram of water from 5 degrees centigrade to 10 degrees centigrade is 42 into 10 to the power 3 joule. This is a very simple question that will help you in building up the concept of how a specific heat concept we can use. Now this data you have to remember. 4200 joule, this is the joule per kilogram per degree centigrade is the specific heat of water, as I told you earlier. Law of mixing that states that when two bodies are placed in contact which are at different temperature, then the one body will lose heat and the other body will gain heat, and ultimately an equilibrium temperature is reached where the both body takes the same temperature. For example, now what will be the time that of getting that equilibrium temperature? That depends upon the nature of body. So here I am taking an example. I am taking an example to show you that suppose you are taking the 2 kilogram of water at 80 degrees C and 1 kilogram of water at 30 degrees C, and then you have mixed them. Then what is the resultant temperature? That means they are asking what is the equilibrium temperature. Equilibrium temperature, that is after mixing. So naturally this body is at higher temperature, this body is at lower temperature, so it will decrease to suppose T final and it will increase to suppose T final. So what we can see? We can see that this will, the amount of heat lost by this body, Q M, I am converting into gram, and a specific heat is 1, delta T is 80 minus T, from 80 it has decreased to T, and this should be equals to 1 into 30 to T, so T minus 30. Here you understand, this is the specific heat. So if you will calculate, we can get 2 into 1000, 80 minus T So what we are getting? We are getting that in this situation we are getting that the heat that it has lost and the heat that it has gained. M, water I have taken, so 1000 into T minus 30 this body has increased from 30 to T, so change in temperature is T minus 30, and this has decreased from 80 to T final, so it is 80 minus T, and making them equal you will be getting that T is 63.33 degrees centigrade. Now this value is there, that we are getting a temperature, that the equilibrium temperature will be this much. The same question can be done in some different way. Suppose I am not taking water, I am taking some different material. Let us suppose I am taking two bodies, same A and B is there, but this time I have changed the specific heat. So here it will be the temperature T final, same question is there, only the specific heat value we have changed. So its temperature will change from 2000 in gram, specific heat SA, temperature change from 80, it will be T final, and it will be 1000 specific heat SB, temperature change T final to 30. This is increase and this is decrease. So what we are getting? 2, 4, 5. Now here you see, this is 2 kilogram. So in this situation what we will observe SA is this. So heat lost 2000 into SA, 80 minus T final, it has decreased, and it has increased 1000 into a specific heat of B into T final minus 30. So if we will do the calculation, 0 will cancel, 2 will be left, SA is your 2 and 80 minus T final, here SB is your 4, T final into 30, so 2 2s are 4 and this 4 will cancel, and 80 minus T final is equals to T final minus 30, so 2 T final is equals to 110, so T final is equals to 55 degrees centigrade. So in this way we can understand that in the law of mixing we can create this type of situation and we can find the equilibrium temperature. Equilibrium temperature is what? That temperature which after mixing the two bodies we are going to attain the common temperature of the system. That is called the equilibrium temperature, provided no heat is being lost to the surrounding or in any other way. Here you should understand, I am taking an example that 2 kilogram of water is there and 1 kilogram of water is there. Its temperature is 40 degrees C and its temperature is 90 degrees C. Here you should understand in a very careful way that if I take, this question can be done in this way, that net, if it is losing heat and it is losing heat and it is gaining heat, then the net heat of exchange of the system should be 0. So if I take a general temperature T, then we can write in this way, MS we can do it in this way also, MST minus 40 plus MST minus 90 should be equals to 0. So if I do it in this way, then we can get T also, that this T represents equilibrium temperature. Here you see, what we will get net exchange is 0. So we can get 2 So So here you try to understand the similar concept is there. Here only I have used, and this method will be helpful to you people in a very comfortable way when you are mixing more than two liquids. So see here what we are getting, if we will take the total heat exchange is equals to 0, then mst minus 40 for this plus mst minus 90 for this must be equal to 0, and if you will solve you will get T is equals to 170 by 3 degree centigrade. And it is very helpful when more than two liquids are mixed. That I will give you by another example. Let us consider that here I am taking that the three liquids are there. In fact, water is there. Three liquids are there. Water is there. So first is your at 10 degrees C. Second is your 8 degrees C, and third is your 5 degrees C. Water is there. Second and third. And here what I would mean to say, that its mass is 3 kg, its mass is 4 kg, its mass is 2 kg. Now in this situation, if we want to final temperature, let the final temperature be, if the final temperature is T, then by law of mixing, we will get mst minus 10, mst minus 8, mst minus 5 must be equal to 0, and we will get the value of T So what we are observing, that the final temperature can be given as final temperature if we consider T minus 10 for this, T minus 80 for this, and T minus 5 for this. This is 3 kilograms, so here 3. This is 4 kilograms, so 4. This is 2 kilograms, so 2. Specific heat remains the same, 1 calorie per gram per degree C. And by calculation we will be getting that T is equals to coming 8 degrees C. So 8 degrees C is that value of temperature. When you will mix these three liquids, then they will attain a common temperature. So this value, this way also law of mixing can be helpful. And you can apply this concept that total heat exchange should be 0. So this total heat exchange, this is the total heat exchange that we have taken to be 0. So in this way also we can solve this question. Now one more last question we should do, and that is also a very good question. Let us see what is that question. Now let us take the example that is very good question. It is a standard question. It will help you in understanding the law of mixing and its application in a better way. There are three bodies of same mass. Here you see mass is same but different material. Different material means a specific heat is different. Different material means a specific heat is different. If we consider the three bodies, the first body has a temperature of 12 degrees C, the second body has a temperature 15 degrees C, and the third body has a temperature 20 degrees C. If A is touched with B, then we are getting A is touched with B, we are getting, if A is touched with B, then final temperature is 13 degrees C. A is touched with B, its temperature is 12, it's 15, so naturally it should be in between, so we are getting the 13 degrees C. And if B and C are touched, the final temperature is 18 degrees C. Your question is, the question says what will be the final temperature if A is touched with C. So in this question we will apply the same concept, that law of mixing is here. Here you see, in first case what we observe, this will gain heat and this will lose heat. So M mass is equal MSA 13 minus 12 must be equals to MSB 15 minus 13. So by this solving you are getting SA is equals to 2SB. Now if we talk about B and C, MSB, specific heat of B, 18 minus 15 must be equals to MSC 20 minus 18, and we are getting 3SB is equals to 2SC. Now if we solve touch A with C and we are applying the law of mixing, the same temperature we obtain, you see, suppose T is the temperature, then MSA T minus 12 must be equals to MSC plus MSC T minus 20 must be equals to 0. As I have told you that sum total heat must be equals to 0. Total heat exchange must be equals to 0. So MSA T minus 12 is equals to MSC T minus, and this way we are getting SA T minus 12 mm mass is equal, so it will cancel. SA T minus 12 is equals to SC T minus 20. At the place of SA we are writing this value, that is 2SB. So 2SB is there, 2SB T minus 12, and at the place of SC we are writing 3 by 2 SB. So here I am writing 3 by 2 SB, so 20 minus T. So ultimately what we are getting, SB will cancel, and 2 2s are 4, 4T minus 4 12 ja 48 is equals to 60 minus 3T, and 70 is equals to 180. So T is equals to 108 by 7 degrees centigrade. This you should understand very carefully, that this question is very good in understanding the law of mixing and its application. So hope this much amount of discussion will certainly help you in building up a better concept of a specific heat. So in the next lecture we will continue our discussion of calorimetry. Thank you. Have a nice day.